Hello students, myself Muhammad Adil Sheikh, an assistant professor of chemical engineering department from LJIET Institute of Engineering and Technology. Today I am going to take a lecture of a mass transfer operations 2, and in this video we will see an experiment that is called as a water cooling tower from the chapter number 2. Okay, so let us start the video. So this is the name of the experiment, that is a forced draft cooling tower. Okay, the aim of the experiment is to study the performance of the water cooling tower, and this is the instrumentation of the water cooling tower as you can see in this figure. Alright, now the working principle of cooling tower. So basically the cooling tower is actually heat removal device that will use water to transfer a process waste heat into an atmosphere, which means that through the cooling tower we will circulate water and air, and so the waste heat, or you can say the heated water or hot water, after mass transfer and heat transfer with the air, it will be cold, and the waste heat in terms of air will be removed to the atmosphere. An industrial cooling tower will operate on a principle of removing heat from a water by evaporating small portion of a water that is recirculated through it. So basically within an industrial cooling tower, the principle is that the heat will be removed from the water by evaporating small portion of the water, and then it will be recirculated in by the means of air. Alright, now this is a water cooling tower. As you can see here that the hot water is coming from the top, okay, and the air which is flowing through the bottom, and after mass transfer and heat transfer with air of hot water, then the hot air will be discharged from the top, while the water will be cooled down and it will be collected from the bottom. Alright, so this was a working principle of cooling tower. Now the construction of the cooling tower, or you can say the equipment which was used for the experiment. So this is the basic construction, that the cooling tower is actually constructed as a cylindrical, and it will be having approximating of 150 mm to the 150 mm to the 650 mm in height. The packings which are used within the tower are CU plates. Alright, now the air which will be passed through the cooling tower by the means of air compressor. Okay, then the cooled water will be removed from the tower, from the bottom of the tower. Then the hot water was fed via valve and a rotameter which was arranged at the bottom. Then there was a water storage tank around 100 liter of the capacity, and it will contain an electric heater at the bottom, alright, for the temperature control. Then the heated water was pumped through the pump from the storage tank, and it was entered through the tower via distributor at the top of the cooling tower. Then the temperature of the inlet and outlet water as well as air was taken in the closed tower. Then at the end we will find out the temperature of the inlet and outlet water and as well as air. Okay, so this was about the cooling tower, and this is how the equipment will look like, which was a forced draft cooling tower, or you can say water cooling tower. So here you can see at the bottom there is a storage tank or feed tank, and it is connected by the temperature controller, or you can say heater, and it eventually it is connected to the pump which is used to pump the water, or you can say hot water, to the top of the cooling tower, and from the top it will pass through these packings, and it is collected at the bottom. Now here when the air compressor is provided at the middle of this, or you can say at the bottom of the tower, so that the air will flow upward within a manner, and the hot air will be removed from the top of the tower. There are thermocouples which are installed at the inlet and outlet for the temperature measurements of both water and air. Now the experimental procedure of this cooling tower is that first of all we will fill the storage tank with the water, and then we will switch on the heater. Alright, and we will set some sort of desired temperature within this heater. After that we will close first delivery valve, and we will regulate the water through the tower, so that we will obtain the uniform temperature within this. After the achieving the desired temperature, we will switch on the air compressor, and then after we will allow the air to flow within this through the bottom. Okay, after that we will note down the inlet temperatures of air, both dry bulb and wet bulb temperatures, and after that we will switch on the pumps, and so that the desired flow rate will be set through the rotameter within the range of 0.3 to 3 lpm. After that, by using a delivery valve and also by the rotameter, that is over the delivery line, we will note down, we will adjust the flow, and then we will note down the inlet temperature of a hot water, that is a T1. Then we will allow this tower to run within this same condition for at least 10 minutes, so that we can achieve a steady state condition. And after that steady state condition, we will find out, or you can say we will note the outlet temperature of a water and air both. Okay, and here we are not required to allow the hot water inlet temperature to overshoot or to undershoot, and also we have to keep eye over the heater, so that we can switch on or switch off at that time. Alright, now after achieving the steady state, we have to note down the temperatures of both water and air at a outlet. Alright, then after we can change the flow rate of the water, or either we can change the inlet temperature of the hot water, and we can repeat this entire experiment. Alright, now let us switch to the working of this experiment. Now the working of the water cooling tower. Okay, so within this video you can see that first of all we will switch on the main switch, and so here this is the feed tank which is filled with the water. Okay, so this is a normal water, and this is a temperature indicator, or you can say heater. So first of all we will start this, and we will maintain some of the temperature, or we can adjust the initial temperature. Alright, this is a temperature indicator for the different channels. Alright, so by using this knob, you can see that we have started this heater, and we have adjusted its initial temperature. Now this is a water rotameter, and this is a temperature indicator, and there are some switches for the blower, pump, and also for the heater. Okay, so this is a motor which is used to pump the hot water from this feed tank, and this is a delivery valve which is fully closed right now. So the entire water is being pumped through this pump by and then it is passing through this rotameter, and after this through this pipe it is fed to the top of the column. Alright, so the hot water will be entering from this top of the tower. Now you can see here within this glass shield, that the water is flowing downward by passing through the packings. Alright, and so the hot water is flowing downward, and through this valve which is being installed here, yes, you can see through this pipe it is flowing back. Alright, now these are the some temperature indicator instruments which are being installed at a different locations, as you can see here, which are being connected to the main temperature sensor. Okay, this is a thermocouple which is being installed at the bottom of the tower. So this is a cloth wick for the wet bulb temperature, and these are the thermocouples for the wet bulb and dry bulb temperature of the air. So at the top of the column also there is a two thermocouples are provided for the wet bulb and dry bulb temperature of the air. This is a temperature indicator, alright, for the different channels which will indicate the temperatures. Now initially this is showing the temperature of a hot water, that is 43 right now, that we have adjusted earlier, and so we will start adjusting this flow of the water. Alright, first of all we will switch on the blower so that the air will be flowing through this. Alright, so the air will be flowing through the bottom of this column, and by now after that we will maintain, or you can say we will adjust the water level within the column by using this water rotameter. Okay, so that we can have the flow of the water through the column. Now we will note down the three different temperatures, that is this is the hot water inlet temperature, the channel 2 will indicate a dry bulb temperature of the inlet air, and this channel 3 will indicate the wet bulb temperature of the inlet air. Okay, so like this we will note down these temperatures. Now after some 10 minutes or you can say steady state, we will again note down the temperatures, but now this time for the outlets, like cold water outlet and also the air outlets. So this channel number 4 will indicate the wet bulb temperature of the outlet air. This 5 will indicate the dry bulb temperature of outlet air, and this 6 will indicate the cold water outlet temperature. So as you can see, the cold water temperature is less as compared to the hot water inlet, and so we can say that the water is being cooled by using this water cooling tower. Now again, after some time, we can adjust the water rotameter level, or you can say we can adjust the flow of the water to some another values, and then also we can, after that we can take the temperature readings. So again, we'll take the 3 temperature readings, that is number 1, 2, 3, that is a hot water inlet temperature, then dry bulb temperature of the air, and also at a channel 3 the wet bulb temperature of the air at a inlet. And then after 10 minutes we can find out the outlet temperatures of the water and air. So after this we can find out like this for the channel number 4, 5 and 6, that is a wet bulb temperature and dry bulb temperature of the outlet air, and also the cold water in outlet temperature. So as you can see here again, that the cold water temperature is less as compared to the hot water inlet temperature, and so that we can say that the this water cooling tower is properly functioning. Alright, and we can also say that the air temperatures are different, or you can say are increased than they are at a inlet temperatures. Okay, now there are some data given for this cooling tower, that the cross sectional area which is given, that is 150 by 150, and it is 0.0225 meter square. Then the height of the cooling tower which is given as a 650, or you can say 0.65 mm or 0.65 meter. Then the latent heat of water at 0 degrees Celsius, which is 1184 joule per kg. The specific heat of air, that is 1003 kilojoule per kg. Then the specific heat of water, that is 2.006 kilojoule per kg. Then the specific heat of water 4.18 kilojoule per kg. Then flow out of area for the air, that is a 0.1 by 0.1 meter. And then molecular weight of air and water, that is 29 and 18 respectively. Alright, after that we have to draw an observation table, and this will look like this. Okay, now the air velocity will be constant because we will use a constant air compressor, and so it will be somewhat around 1.5 meter per second. Then we can adjust the flow of the water, that is in LPM, or you can say liter per minute, and we can adjust the flow through the rotameter, and we can find out the different temperatures. So first of all, we have to note the inlet temperature of water, T1, then inlet temperature of dry bulb and wet bulb temperature of air, that is T2 and T3, and after 10 minutes we have to find out the outlet wet bulb dry bulb temperatures of the air, and also the outlet temperature of the water. So here when we will use the cooling tower, the inlet temperature of water will be high, but at the exit temperature of the water will be low because of the cooling tower, and also the inlet temperature of air will be high, will be lower, but after the or you can say the exit of the at the exit of the tower, the temperatures of the air will be higher because of the heating. Okay, now switching to the calculation portion. Now the flow of air will be velocity into area. Velocity is 1.5 and area is 0.12 into 0.1, and so the flow of air will be 0.015 meter cube per second. Then the flow of water, so the flow of water in LPM multiplied by 10 to the power minus 3 divided by 60, and so it will be 0.0833 kilojoule per kg per second. Then the dry bulb and wet bulb temperatures, and then absolute humidity Y dash, which will be mass of vapor per mass of gas, and it will be 0.018 kg per kg water per kg dry air, and molar absolute humidity will be Y dash into MB upon MA, and so it will be 0.029 kilomole water per kilomole of dry air. Then after the PA, which will be calculated from the absolute humidity, and so it will be 0.029 multiplied by PT, which is 760 mmHg, so it will be 101325. Okay, and then divide by 1 plus Y, and so it will be 2855.75 Newton per meter square, or 21.41 mmHg. Then LNPV, so from the Antonis equation we can find out the vapor pressure, that is 21.97 mmHg. Then the relative saturation, that is PA upon PAV into 100, and so it will be 97.45%. Then the percentage saturation, that is Y dash upon Y multiplied by 100, and so it will be 62%. Then the humidity volume VH was calculated by this equation, that is 8315, and multiplied by 1 upon MB plus Y dash upon MA into TG plus 273 upon PT, and so it will be 0.865 meter cube per kg of dry air. Then after we can calculate this humid heat, that is CS, which is equals to CB plus Y dash into lambda, or you can say E, and so it will be 1038.91 joule per kg dry air into Kelvin, and this one is for the wet air. Then the enthalpy of inlet air stream, that is Hg1, which is equals to Ca into T3 plus Y1 into lambda plus Cv into T3. Okay, and so it will be 100.4123 kilojoule per kg. Then the for inlet air, the water vapor Y1, that will be 0.029 kg per kg of dry air, but in terms of mole it will be 0.048 kilomole per kilomole of dry air. Now the flow of dry air will be 1 minus 0.048 multiplied by flow of air, and so it will be 0.01428 meter cube per second. Then after the density of the air at a T3, so it will be 29 multiplied by 273 upon 22.4 multiplied by 273 plus T3, and T3 is 24, and so it will be 1.17 kg per meter cube. Then the mass flow of dry air will be G dash, and so it will be rho into flow of dry air, and so it will be 0.017 kg per second. Now the slope of operating line, that is L into C1 upon G dash. Okay, so we have calculated all these things, and so the slope of operating line will be 2151. Then the coordinates of the bottom of the operating lines will be T3, that is 24 degree, and Hg1 will be 100.4123 kilojoule per kg. Now the enthalpy temperature diagram, the operating line of the slope, it will be drawn through this point, that is T2 Hg2, and so it will be 30 degree and 106.7454 kilojoule per kg. And when we will draw the enthalpy temperature diagram, it will look like this. Okay, and this is the operating line. Now the top point of the operating line was temperature, that is 43 degree, and Hg2 is found to be in kilojoule per kg. And then we can draw the tangent of this enthalpy temperature curve, and we can find the slope, which is similar to the line which is connecting the inlet and outlet conditions. And we can also find out the slope of the operating line, and we can calculate this slope. Now the ratio of the slope between saturation and operating line ratio should be nearly equals to 1. Alright, so this was about the calculation portion, and from this experiment we can say that when we will contact water and air, then the hot water will be converted into cold water by rejecting its heat to the atmosphere or air, which was actually the working principle of the cooling tower. Alright, so about this was it about this experiment. Thank you.